Good morning, everybody. This time is yours. What do you want to ask me? 42 is the answer to that question. Yeah. The answer to life, the universe, and everything is 42. Or the square root of 2gh.
Will the integral setup, will that be multiple choice or like?
It probably will be on future exams. This one it is not. You give a situation, set up the integral. Don't do the integral. No. You will waste time. You've got better things to answer.
Can we practice on arc-to-arc problem?
Sure. The conceptual one is multiple choice. Yeah, if it says conceptual on it, it's a multiple guess problem. That's how you know it's a conceptual question. What do you have to do with conceptual questions? You must explain your reasoning, right? You choose, and then you tell me why you chose what you chose.
What if you guess right, but your reason is wrong?
Then you're dead. Because I check.
Can I ask you a question on one of the conceptual questions from the homework?
Yeah, you can ask me anything.
It's from chapter 22. It's the first one.
Chapter 22, conceptual question numero uno. 22. I will just go straight to it. You said the first one, right?
Yeah.
Oh my goodness, what's going on here? 4 situations in which all these charges are evenly spread out with all different charges. Rank the situations using Olympic scoring rules. That's what all of that says right there. Okay? And we are just ranking the magnitude of the electric field at the central point, right? Make that a little bit bigger. And then let me see if I can. Oh, I'm doing this wrong. Give me a second. Give me just a second. I'm supposed to be doing it from my iPad. Darn it. I'm worried because I didn't test this morning. All right, it's going to work. Whew, that was close. All right. And then
I think it's after 6 p.m. Their library closes at 11, but after 6 p.m. I think it's marked there. I don't know.
This is what I have to do in order to get these problems into a place where I can work on them. All right. So we're looking at the central point. So from this charge, what direction will the electric field point? Away, right? And then from the next charge, which way will it point? Towards, but it's going to be bigger, isn't it? Because it's closer. What do you mean what?
Oh, yeah. For a second, I was confused, but now I'm not.
Now you're not. Small red one, bigger blue one, because it's closer, right? As a matter of fact, it's twice as close, which means it's going to be 4 times as big. All right? The negative E right here. Towards and just as long as the other blue one, isn't it? And then the positive E. And the same length, isn't it? So what's the net electric field there? 0. All right. Next line. Positive E on the left. Positive E next left. 4 times as big. Now that I've drawn that over, those are both negative. So which way will those be pointing? Towards and towards. It's negative, right? It points towards the negative charge, doesn't it? And I drew those backwards. The big one should be first, and anyway, it's all the same. All right, C, the negative one on the left over here. Which way will that point? Towards it, and small. The positive E, away and big, right? The positive E, away and big, because it's closer, right? And then the last positive E, away and small. All right, and then the bottom. Negative far away is going to be towards but little, and then towards but big, and then positive E is away and big, and negative E is away and small, right? So they wanted us, and I didn't write it down, they wanted us the magnitude of the field or something, right? So we got to rank these. So this is 0. This is humongous. I don't know how to spell it. Okay. This is also humongous, but negative humongous. And then this is middle. Well, direction may not matter. Did the problem ask for magnitude? Rose, you remember?
Oh, no, it sure did.
It just said to rank them.
Well, it says rank the magnitude.
Rank the situation according to the magnitude of the net field at the central point. Net field at the central point. This one and this one are equal. They're both humongous. This is the next smallest. The middle one's the next smallest. So the two humongous get first place. They share the gold medal. And under Olympic scoring rules, if you have 2 gold medals, what's the next medal that's awarded? Bronze. You skip silver. Okay? And then that one. So that should be the answer. It's not on yours?
I have a greatest, a second, a third, and a fourth.
That's how they grade it.
Greatest, third, second. So they said D was second, B was greatest, C was third. Then I've done it totally wrong, or they're totally wrong.
I did what you did, and I was tripping. You said you're wrong. You find out while he's mad too.
What? Yeah? Oh! Oh! Thank you. I'm a failure.
You got it right faster than I did.
So that's number 2. Isn't it?
Yeah. So there's this.
It's got 3 pointing in the same direction, then a small one. The biggest one's got all 4 pointing in the same direction. Nope. Nope, I'm wrong again. That's not number 2. This one is 2 smalls pointing to the left. This one and this one cancel each other, right? So that's 2 smalls pointing to the left. This one cancels, so this is 2 big ones pointing to the left. Oh, I was right. This is number 2, this is number 3. Is that the answer? Okay. Thank you. See, I can pass any test with you guys helping me. Did I answer your question, Rose?
Yeah.
Okay. Other questions?
I feel better when I see him as an exception.
Yeah. Why do you think I make mistakes? It's all planned, of course. I know exactly what I'm doing at all.
Will the conceptual be like?
It'll be exactly this question. No.
Some of those on 23, the conceptual.
Don't like them?
I don't know what else doing, but
Do we need to go over them, or
we should.
we should? Guys, you're getting to see how the sausage is made.
Oh, I didn't finish it. I was like, damn it.
We'll go student view here, because this one's still. Wait, was this due? When's this due? Yesterday. Oh, well, you guys know all the answers now. Monday. It was due Monday. What's today? Tuesday. That would be yesterday. Jeez. Doing good this morning, aren't I? Figure shows 3 cylinders, which look an awful lot like spheres. 3 surfaces. Rank them according to the electric field at any point on the surface. They are all the same. Why are they all the same? Because the electric field is going to depend, according to Gauss's law, and I know it's Gauss's law because it's a Gaussian surface, right? Gauss's law tells me the electric field magnitude is going to be dependent on the charge enclosed. Right? Now, what about the E in it? Nope. Nope. God, hit the right button, Mr. Balogh. So, right, we have these 3 charges that are all like different sizes, but we have exactly the same size Gaussian surface around them, right? Okay, those are all the same, right? Okay. It's EA equals charge enclosed over epsilon naught, right? Technically big integral on the left, but I never write it that way. Okay. Since this area is the same, and since the charge enclosed is the same for all 3 cases, what is the electric field going to be? The same. Job done. You guys don't want to believe that it's that easy. That your brain is fighting against Gauss's law because it seems complicated or whatever, and it's got these weird esoteric Gaussian blah blah blahs, but it. Did I use the right word? Yeah, well, no, it's just esoteric just means strange and not normal. Figure shows 2 Gaussian spheres, that must be the yellow and the green one, and 2 Gaussian cubes, the blue and the purple one, with a positive charge. Rank the net flux through the 4 Gaussian surfaces. What's the answer? It's the same, because the flux, EA together is flux. The flux is equal to the charge enclosed divided by epsilon naught. Is there anything on the right-hand side of that equation that says the size of the charge, like the size of the Gaussian surface matters? No. Charge enclosed is the same, so the flux through all of those surfaces is exactly the same. The flux, notice it's flux, it's not electric field, right? But E times A. Integrated over all that stuff. Okay. Rank the net flux. We did that. Rank the magnitudes of the electric fields on the surfaces greatest first. Oh, well, this one's even super easy. I don't even need Gauss's law. They're asking me for the magnitude of the electric field. Where's the electric field going to be the biggest? Closest to the charge, right? So it just goes A, B, C, D. Just moving outward. That is not a Gauss's law question. Indicate whether the magnitudes are uniform or variable. There's only 2 that are uniform. It's the circles, the spheres. Uniform meaning the same everywhere on the sphere, right? The reason being is that the point charge electric field has that radially symmetric bad hair day pattern, right? And circles are the only thing that if you draw around that all the vectors are pointing the same way. When you draw the cube, though, you have the surface and you've got like electric field going through at an angle. In fact, where's the only place where the electric field is perpendicular to the cube? I can't draw it on the screen, but it's at that directly away from it's like the midpoint of the side of one of these cubes. That's the only place where it will be pointing directly perpendicular. Everywhere else is going to be a different direction, and so their form is going to be variable. It's going to be different at every point on the surface of the cubes.
Did we cover like how to calculate that?
No. We avoid it by drawing a sphere instead of a cube, right? To make sure EA, it becomes nice.
How would you add up all those charges, the integration of all the charges differently?
It's not the charges that are different, it's the angle between the electric field and the area vector. This is not needed for the exam. But what you would do is if you went on in physics and took electricity and magnetism in your junior or senior year, you would start writing, well, you wouldn't even use this math, but the closest thing that you guys would know to do is that you would be doing this, where you have to know how the angle changes at every point on the surface of the cube. Because this angle is going to change depending on where you are. So it actually becomes worse to do it with an integral, and it becomes better to do it with a differential equation. And some of you I know have seen this in your math. Was it 6? If you've taken, is it math 6 where you do the del operator? Yeah, okay.
Or is that not the gradient?
It's one way to talk about it. We call this the divergence in physics. The gradient is not a dot, I think it's just acting against, but
Way to apply divergence theorem to this stuff?
So if I learn that way, is it easy?
yes, a lot easier. But math 6 is not a prerequisite for this class. More on that at the end of this semester. Oh yeah. Wait, you should see what the physics 2B students do. They don't have calculus. And so I have to write down, Gauss's law has to be written down as the sum of EA cosine theta equals charge enclosed over epsilon naught. And they have to do sums. Yeah. That's why I say 2B is harder. You don't have calculus. All right, more questions. We didn't do all the conceptual questions here.
We didn't do all.
That's okay.
I forgot what number it is on 23. It's the one where the Gauss sphere is a cube and the vector has a y squared in it.
The Gauss sphere is a cube. That's interesting.
The Gauss's surface is a cube, and then the vector is something. The electric field is given in vector form, where one of the vectors.
Oh, yeah. This one.
Yeah, I was gonna ask, are there going to be problems similar to that on the exam? No.
No, it's a good exercise though.
Oh, thank God. Thank you.
This one took about 2 hours.
Yeah. Other questions? Yeah.
Number 9 on 22.
22?
Just how to do it. Yeah, the one that took us like 4 hours. They were like,
That one. The one that took me my life.
no, literally, I was sitting there and I was staring at it and I could feel like my soul just leaving my eyes.
What number was it, Ramsey?
And I barely understood it, so you're good.
Right? Oh, yeah. I'm looking at it.
All right. It's hard for me to shout when everybody else is talking. Is it this one, Ramsey? Yeah, that one. Okay. I am going to point out that in all of the problems now, all the chapters you've studied, there should be a button now that says solution. This doesn't just show up for me, it shows up for you after the due date, right? So you can go here and you can see what they did. This probably doesn't help, right? And I will explain it, right? Okay. But the solutions are there to see how the graduate student who solved the problem did it, right? Okay. It's how that's the instructor solutions manual is just pay graduate students food money to solve problems. All right. I never did that. I reviewed the text. I reviewed the sample problems. I came up with sample problems. One of a college student from my church congregation came up to me during Thanksgiving one time, and they're like, "We saw your name in our physics textbook." They were taking it somewhere on the East Coast. I was like, "Yeah, I worked on that textbook." All right, what am I doing? I'm doing a grab. It was a Physics 2 textbook, I think. And I was listed, like in the 200 contributing authors, I was listed. I think I had worked on 3 chapters in that book. And no, I'm not going to write a book of my own.
Sounds like hell.
No!
It sounds like hell. It sounds like hell. The law of never writing a textbook.
I can finally give the units of momentum their proper name. Balogh. Kilogram meter per second is a Balogh. No, so the problem with authoring textbooks, number one, you have to write. And I can't stand writing. I just can't. Get ChatGPT to do it? Okay. The other thing is you become a slave to the publisher for the rest of your life. You have to do new editions. You have to change things. You have to edit, new edits. They want new pictures. It is. I got a touch of that. A good friend of mine owns a publishing business, came up to me. He's like, hey, do you want to publish a physics textbook? I'm like, no. I cannot stand writing. I just can't stand it. It's physically painful for me to write stuff. I do write letters. And it hurts. But it hurts. So I have a learning disability. Many of you know that. It's related to dyslexia. It's in the dyslexic family. I don't see things backwards or anything like that. But I have a motor problem with my brain to hand writing or typing. It's like hurts for me to get words out onto the page, which is why I don't like emailing you guys. So, as soon as I know that I am writing, like it's going to be written words, my brain just breaks.
That connection is
Just takes a while. I've overcome it over the years, and I just kind of brute force my way through emails and stuff like that. But you've seen my handwriting; it's terrible. That's part of the problem, right? So. But the act of writing it's like painful, mental and emotional, physical torment. I just can't. But as soon as I start dictating something, I get my words just, yeah. This is why whenever I talk in public, give lectures, give sermons in church or whatever, it's just a series of notes. So like my notes are just like, there isn't full stuff on what I'm teaching here. It's like highlights. I fill in the blanks in real time. So, and I do the same thing everywhere. In church, it's just a list of scriptures or quotes to share, and I fill in the blanks. All right. What's that? Sure. Every Sunday. All right, what are we doing? I can let you know after. So what classification of shape is this? This is an arc, right? This is an arc of charge. And I just realized I have my physics 4A notes. Aren't going to help me. Oh yeah, that's what my lecture notes are. These are my cheat sheet, right, for lecture. That's all it really is. All right, so arc of charge. Where's arc of charge? Line, the doodad, arc of charge, okay? And on the arc of charge lecture, it's also in the book, but I do like my version better because I understand it better. I had K lambda over R between two angles, and then there was a negative sign out here, and it was cosine theta I plus sine theta j d theta. That's like the setup. Okay, so I've got two arcs of charge here, don't I? So let's see if we can take advantage of what we know about positive and negative charges. So at point P from the top arc, just this top part right here, which way would the electric field point? At this point, it would go directly down. Why would there be no x direction? Yeah, all the x's are going to cancel each other, aren't they? Because from this top part, I have like a vector there, vector there, vector there, right? There's all the, like if I just look at all these little points, right, going in there. So I know that by symmetry, I'm going to have it all pointing down from the top. Now, what about the bottom arc? It points towards it, doesn't it? But again, the x components are going to wipe themselves out, right? So I can make an argument. By symmetry, the I hat components are going to cancel each other out. Now, if I set up the integral and I do it mathematically, it will happen. The cosine theta is symmetric about two angles that are, 0 to pi, right? And so when you evaluate that, you get a 1 minus a 1, and that ends up being 0, right? Okay? So I'm just arguing, and this is what physicists do all the time. Okay? We avoid math by saying, well, symmetry. And then the mathematicians sit there and go, well, prove it. And we're like, no. Still works. Okay. So we say, no, you prove it. And then they sit down and happily do a cosine integral, and they're fine.
I like how I don't want to. It's perfectly acceptable in physics.
Because the universe does it. That's our answer all the time. Sorry, I misspoke. When you integrate the cosine, it's sine, and sine is 0. Anyway, it all goes to 0. I might as well have just done the integral and shown that. Anyway. Okay, so that means that we are going to do, to get this magnitude, k lambda over r. I'm not going to put the minus in because the minus is just acting on a direction, isn't it? And I'm not going to include the j hat. I know it points down, right? But I do have to double it. Why do I have to double it? We said, right, there's a vector from the top and there's a vector from the bottom. They are all equal because the charges are equal, all that kind of stuff. Okay, so then integral of sine theta d theta, and what are my angles? 0 to pi. You can do 0 to 180 if you wanted to. But okay, so that's equal to k lambda over r. Integral of sine is cosine? I know it's cosine. The problem is it positive or negative? Is it?
Yeah, it's negative cosine.
I don't care.
It's a negative cosine.
Negative cosine? It's just a direction. Evaluated from 0 to pi, so that's negative of a negative 1 minus 1. No. Negative of a negative 1 minus 1, which is 2 with a negative sign on it. That becomes positive. I hate directions. Okay. So that's 2. I'm doing this very sloppily. So this is 4k lambda over r, isn't it? So that should be the answer. 4, 9 times 10 to the 9. What are we going to do for lambda?
You can solve it.
It's q over the length, isn't it? It's supposed to be an L. What's the radius of this thing? 0.0741. Okay. What did I just do to the 7.41? Why do you have to put it in meters? Everything needs to be in standard units. Otherwise, constants and things aren't going to work. Okay, so the Q over L, the lambda, is 13.5 times 10 to the minus 12. Okay, I told you guys that you only need to go up to nano, right? So if I give something on the test like pico, and you can't remember what that is, what are you going to do? You're just going to come up and ask me, and I'm just going to tell you. Because you're on the hook for 10 to the 9 all the way down to 10 to the minus 9, including centimeters. Right? So, but pico, femto, atto, we use them sometimes, but not all the time. All right, divide, and what's the length? It's the arc length, isn't it? Okay, so that's going to be 2 pi r divided by 2, right? Yeah.
Oh, 2 pi r divided by 2.
Right, it's because a circle is 2 pi r, then we cut it in half, divide by 2. You can just get pi r. So I'm going to stop. I'm not going to. This goes here, and you get 28.1. I hope. I'm pretty sure that's it.
All the homework gave us like nice, like theta 1, theta 2. On the exam, we also get like nice angles.
They're all nice.
All nice.
What do you have against pi over 32? What do you mean by nice?
Like 0 to 90, 0 to 180.
Oh, yeah. We'll try to keep it quarters and halves and 3/4 and yeah.
I don't like obtuse angles. So.
Can you do an example of like putting a charge on a line where like the electric field is 0? Like, do you know what I mean?
Oh, like that we've done 3 times now.
It's just difficult to think about because it could be anywhere.
Okay. All right. So, and you guys had this again with the Gauss's law homework. It was just the 2 spherical shells. And the trick there was to realize, well, they're just point charges. Anyway. Okay. So you guys tell me. Here is a x and y axis. Where is one of the charges? At the origin? Okay. Positive or negative charge? Negative charge. Minus Q1. All right, where's the other one? Right or left? Right? Positive or negative? Positive? Okay, Q2. Doesn't matter what the numbers are, just kind of need to know the sign of the charge. Okay? Actually, it does matter what the numbers are. Which one's bigger charge magnitude? Or are they the same? Same is easy. There's no solution. Yeah, I don't think there's a solution. I'll prove it. I'll prove it in a second, but I think you can't do that. Q1's bigger? Okay. So Q1's magnitude of charge is bigger than Q2's magnitude of charge. All right. That means that there are 3 regions. Roman numeral 1, Roman numeral 2, Roman numeral 3. Getting fancy now. So the region 1 is from the origin all the way to negative infinity. Region 3 is from Q2 all the way to positive infinity. And region 2 is between the charges. I know that the 0 point for electric field cannot exist between the charges. Why? No matter where I pick on this line, okay, the electric field from the positive charge points which way? And the negative charge? Towards. No matter where I do it, right? If I do it here, it's towards, and from the other one, it's still there, right? Okay, over here, that way, and that way, no matter where I pick, anywhere in region 2, the 2 vectors, the 2 electric field vectors, cannot add up to 0 because they're pointing in the same direction. So what does that mean about region 2? Can't be there. Which region do you want to do now? 1? You guys are being boring. Okay. Region 4. Why not? So what direction is the electric field vector pointing for the blue one? Towards it. And for the positive one? Away from it. Can we get 0? Yes. Those 2 vectors are in opposition to each other. There is the possibility for getting 0. We haven't checked magnitudes yet. We're just checking the direction. What about region 3? Still can be in opposition, right? The negative will be pulling towards it, pointing to the left. Positive will be pushing away towards the right. Okay? Now, how do we know whether it's region 1 or region 3? It's the distance and the magnitude of charge that matters now. Because we want to be as far away as we can get from the bigger charge. Why? The electric field magnitude goes as charge, directly proportional to charge, but inversely proportional to distance. So we want the bigger charge to be further away. So what region puts the bigger charge further away? Region 3. We get close to the smaller charge, right? The smaller charge, we'll make up the deficit of the small charge with being closer to it, right? All right. So that's the theory behind it, right? You identify what regions it can be 0 in, and then you take a look at magnitude of charge and distance and get closer to the smaller charge. Okay. So now, since we know it's region 3, okay, we could get really specific here, but in the end, what do these two magnitudes have to be? Equal to each other, don't they? In order to add up to 0, we need a situation where we have kq1 over r1 squared equals kq2 over r2 squared. You can get there by doing this, right? And if you move this over, you get minus e2 equals e1. You're like, what's the minus sign? One of those is pointing the opposite direction, right? So they're both, the minus sign is going to cancel itself. All right. So we know those two magnitudes have to be the same. So now we need to figure out what R1 and R2 are. So I'm going to redraw my picture here, just because I messed that one up and made it all dirty. Minus Q plus Q. And I know I am right here somewhere. Okay. So what's the distance from charge 1? Where is that green dot located?
1, 2, 2 plus whatever.
It's just located on the x-axis somewhere, isn't it? Charge 1 is at the origin, so it's just x, wherever it is, right? Okay, so this is equal to x. Where is R2? Where's that distance? It's here, isn't it? Right? It's the distance from charge 2. This is charge 2. This is charge 1. So what is that distance?
X minus the first.
Okay, so if we call the distance between the charges L, right? Then this distance in here is x minus L, isn't it? So this is x minus L. So now I rewrite my equation. kq1 all over x squared equals kq2 all over x minus L quantity squared. And the panic begins to set in at this point. Why does the panic begin to set in? Quadratic, right? It's looking quadratic to me. That x minus L squared, I'd end up with x squareds and L squareds and XL things, and it's looking bad, but I'm going to show you a way around it. Are we okay up to this point? Is everybody following? Those of you that aren't, just going to suffer in silence? Good? All right. Can I get rid of k? Same on both sides, isn't it? And then, show you a trick. If I take x minus L squared all over x squared equals q2 over q1, what did I just do? I moved that up there, and I took the q1 and I moved it down there. You may have learned divide everything by q1, right? Or multiply everything. It's the same difference. It ends up functionally doing the same thing. Okay? So I just kind of swapped places with them. And the reason I did that is I wanted to get all the squared things together on one side of the equation before I go like squaring, doing FOIL methods and all that kind of stuff. Because now that I have x minus L squared and x squared, isn't this the same thing? Yeah. Okay. So if I take the square root of one side, what do I do to the other? Take the square root also. So what does the left-hand side turn into? Just turns into that, doesn't it? And then over here, What is everything on the right-hand side of this equation? A number. Right? Can I take the square root of a number? As long as it's positive. Right? Now that does bring up an issue, right? Okay, because Q1 is negative, right? But in this problem, did I start with a E vector, with an R vector, R cubed, blah, blah, blah? Notice I'm not using my R vector method for this, right? This is just magnitude of electric field being equal to each other. So when I go for the charge, am I going to put in the magnitude of charge or the sign of the charge? I'm dealing with magnitudes. I'm only going to put magnitude of charge in. I've already dealt with the directions that are caused by the signs of these charges. All right. It's not that the R cubed, R vector thing wouldn't work. It's just it's way too formal for this way of going about it. It just adds 10 steps before you get to what I have right after Roman numeral 3. Okay. So that's just a number. Let's see. We need to get x all by itself. So I got some algebra to do, right? So x minus L is equal to x times this square root 2 over 1. And then let's see, if I move this across the equal sign, and then I move the L across the equal sign. If I take a negative L over here, what happens to it? Becomes positive. And if I take this positive thing over here, it becomes negative, doesn't it? So now what can I do with these x's? Factor them out. 1 minus the square root of q2 over q1 equals L. And now what's everything in the parentheses? A number. So I'm going to take a number and divide it by a number. That square root's supposed to go all the way down. There we go. There we go. For this particular situation, that is the solution. All right, let's take a look at this. What if Q2 and Q1 were the same magnitude of charge? Somebody said let's make them the same, and I said it's impossible.
Would be something over 0, right? You can't have
Same magnitude.
So if Q2 and Q1 are the same magnitude, the same number, then what's their ratio? Q2 over Q1 would be 1. What's the square root of 1? What's 1 minus 1? What's the answer? Okay? Infinity is the end, not undefined. It's infinitely far away, right? So the 0 point would be at infinity, which makes sense. Okay? There is, or in other words, there is no 0. Okay? So now we just play around, and we know that Q1 is bigger than Q2. So this becomes a number, right? That is Q2 smaller, so that's a number that's smaller than 1. So 1 minus a smaller number than 1, square rooted, is still a smaller number than 1, which means that this is bigger than L. If I take L divided by a number less than 1, what do I get? A number bigger than L, right? And is that true? Did I get to region 3? Yes. So whatever numbers you give me, I can figure it out.
When do you recommend using the more simplified point charge version versus the R vector method?
When you know, like, the relationship between the charges. Like in this problem, it said, you know it adds up to 0. I'm not going to waste time with an R vector, and especially if it's all along a line, I don't need R vectors anymore, right? I'm just going to do the magnitudes and figure it out that way. But as soon as I have to do anything that's off of a line, I'm R vector 100% of the time, right? Because now I've got angles, now I have to find components, and I'd rather that the R vector just find the components for me. So that's really the difference. If it's along a line, just do it the simple way.
Then you can use cosine and sine, right?
You can do it that way to find those components. I usually don't. But.
Can you go over the different formulas for the charge distribution for the electric field?
Didn't I do that already? No. I didn't do that already?
We
Was that for 4A that I did that? No. Didn't we do that in one of the labs?
No.
Didn't we write down the equations for all the charge distributions?
We wrote them down, but we gotta see how we
Did we?
For all the like the arbitrage and
Are you guys planting false memories now? No, I'm just old.
we actually never even learned
No, I mean, okay, well, in fairness, I've been doing this for 23 years, so there's a memory in my head of having done this before. Okay, so, Gert, what was your question?
Oh, I wanted to see more integration set up for like variable densities and stuff like that.
Okay, let's see if we can get there. All right, I don't know if we can see all of them. Because we've got electric fields of rings. It's one thing to have the formula, it's another thing to know how to apply it, right? And I reserve the right to write these down wrong. You are responsible for knowing if they're right or not. I know that sounds unfair, but that's just the way it is. Electric field of a disk. This is why I make you guys go through and pull all these out, because I'm pretty sure I got it right in class, and if I didn't, I would have corrected it. Through the power of editing. X over x squared plus r squared to the 1/2. 1. So I've got disk, I've got ring, well, okay, point charge, kq over r squared. Oh, these are all vector things.
Bisector of a rod. On the disk.
What did I do wrong?
Oh, about the bisector of a rod.
Yeah, yeah. So now I have the perpendicular bisector.
That's a 1/2 on the.
Yeah, I know. I drew it kind of badly. That's a 1/2. Perpendicular bisector, I had k q j hat all over y square root of a squared plus y squared. And that kind of assumes that my rod was along the x and the point was along the y-axis. So what happens if the rod is along the y-axis? Just change your j to an I, change your y's to x's, you're done. Okay. And then E field for an infinite rod is lambda all over 2 pi epsilon naught y. J hat, that would be a horizontal rod. The arc of charge, do I have to write it down? I'll write it down again. For completeness, right? Negative k lambda over r theta 1 theta 2 cosine theta I plus sine theta j d theta. I did it in class, but the electric field of a semicircle, well, it turned out to be negative 2 kq over pi r squared, j hat. That one's already done. We did all of those. We did the line of charge. That's just extra notes. So what are we forgetting? Rods, disks, rings. That's the point charge.
Planar charge?
Oh, yeah, that's just.
Well, so this is all chapter 22, right? For 23, your Q enclosed can have all of the rhos, sigmas, lambdas, right? And then you've got spheres. I swear I remember doing this with you guys recently. This is Q over V, Q over A, Q over L, and then you've got like, so for the sigmas, you have like you could have a surface area of a sphere, right? So that where your dq is equal to sigma dA, and that could be sigma 2 pi RL. What's that one? Surface area of a cylinder. Sigma 4 pi R squared. What's that one? That's a sphere. Surface area of a cube.
It's the area times 6.
Yeah, xy, 6xy, isn't it? Sigma 6xy cube. And then for the volumes, your dVs, your rho dVs, right? For the sphere, it could be 4 pi r squared dr. That's really the most common one for the sphere. It's the one we use kind of all the time. There's other ways to cut spheres, but they're not nearly as useful or nice. What would it be for a cylinder?
2 pi r.
It can be 2 pi r. So that would be its circumference times L. And then you could do a dr. That would be a volume. It could also be pi r squared dl. That's like a cake layer, right? So the 2 pi RL dr would be like toilet paper rolls, nested toilet paper rolls. And the pi r squared dl would be slicing cake layers up the cylinder. I think those are like all of it. Slicing a cube is just in a dx or a dy.
What's the
What's that?
I thought there were no cubes in the. Are there cubes?
Could be. Sometimes useful for Gauss's law. The other thing we got out of the Gauss's law chapter were like electric fields for a line of charge, which we've already written down. We picked up the electric fields of planes. So for the thin plane, it's sigma over 2 epsilon naught. And for the thick plane, it's sigma over epsilon naught. Did I get that right? Yeah.
What is phi again? Or phi?
Capital phi is the flux.
Capital phi.
So where are you going to be integrating for chapter 23?
The Q.
It's the Q enclosed, right? It's finding the charge enclosed, which I covered in chapter 21. I first introduced you to that in chapter 21. So you might want to check the chapter 21 notes for all the different ways. No, we reserve that for Gauss's law. So if you're being asked to find the electric field inside of a charged object, are you going to use chapter 22? No. What are you going to use? Gauss's law. If you're inside, just use Gauss's law. If you're outside, it can be faster to use Gauss's law than to use chapter 22 stuff. Now, if you're given, I don't know, 4 charges arranged on a parallelogram or something, is that Gauss's law? No, that's chapter 22, right? So how do you know when to use Gauss's law and when not to use Gauss's law? The answer is, if you can do it quickly with Gauss's law, use Gauss's law. But individual point charges is not easy to do with Gauss's law. There you go.
Is there going to be a question like that? Where we got a random choice?
I just put one question on the exam. It's up to you to figure out what to use. No, I put no. Yeah. So I mean, I don't. Yes, I don't. I can't. Yes. No. I don't know. I'd have to look at the exam. I wrote it last week. That was last week. Oh yeah. I don't have room in my brain to remember last week.
Real. So real.
I got much better things to do with the processing power up here.
What is a electric flux slash Gauss's law problem? Like, what could that look like?
Yes. I mean, it's all your homework from chapter 23.
Okay, so just like, because there was only like really one that asked us to find the flux. It was the cube one.
Oh, maybe I'm telling you, you can, so how do you solve for the flux using Gauss's law? No. You don't use EA to find the flux if you're using Gauss's law. What do? Q enclosed divided by epsilon naught. Because this whole thing over here is the flux. EA is the flux, but the flux is equal to charge enclosed over epsilon naught. Sometimes in the problem you don't know charge enclosed, and so yes, you have to find the flux by doing E times A. But if you are given a charge, and you can draw a Gaussian surface around it, your flux is just the charge enclosed divided by epsilon naught. That's the power of Gauss's law. You know what the flux is if you know the charge enclosed.
Isn't there like a time where like you can't make it EA?
Yes, there's lots of times, but not in this class. At this point, we're making sure it's all EA for you.
And then what's the one where you like it's EDA cosine theta?
That's all the parts that we're not asking you to do. Try to make sure that we use symmetric charge distributions, all that kind of stuff. So, yes?
Can you show an example of variable charge being set up into an integral?
Oh yeah, like doing an integral.
Yeah, basically using the faux and sigma stuff you used.
Can we stay after class for more?
You cannot stay after class because there's another one in here.
They're not important for that class.
They're not important. Tell Dr. Kerfoot that. All right. This is really dangerous because I'm not going to know how to do the integral, but give me a, volume or surface area? Surface?
Volume of cylinder. Yeah.
Volume? Okay.
I would do volume.
Volume and cylinder, sphere, shower, stall, what do you want? Cylinder? Cylinders not start with an S. Okay, so give me a volume charge density function. Like it needs to vary somehow. It could vary in R, it could vary in Z. Let's not do angle. Z cubed? We've done AR squared a lot.
I was saying Z cubed, we haven't done something like that.
It's just made up. AR cubed? R cubed? It's the same as AR squared. Yeah, it does, right? Which number was that? I thought it was 9 that gave everybody trouble. Yeah, except this is a sphere. Yeah, I got a lot of questions about this one. This is a cylinder with AR squared in it. So we'll go back to choose your own adventure. So we would never give you both R and Z, so pick one, R or Z. R. What's the function? This is your chance to like really pin me to the wall. scoring?
A divided by R.
A divided by R cubed? You guys could have given me an exponential. You could have given me a natural log. You could have done anything.
Limit R equals infinity.
No, you've spoken now. Okay, so there's my cylinder. It varies as the radius cubed, okay? Meaning that as I get further out along this radius, it goes from a charge density of 0 at the center, of infinity at the center. Oh, we're going to get a discontinuity. Never mind. It's okay. And then, so, okay, wait a second. This is not physically possible.
R plus 1.
Yeah, it's got to be, it's got to be more along the lines of A over R cubed plus a number. Because we don't want infinite charge density at the center. That would be bad. Okay. So we'll do that right there. Or do you want R plus B cubed? I don't know. We'll do this. Okay. So the R in there, the fact that it varies as R tells me what I'm going to do to cut this thing up. How are we going to cut it up? We want dq to be equal to rho dv, but it's got to be a volume cut up so that I take advantage of R, right? So I know it's going to have a dr in it. So now I need to build a volume out of dr. It's going to be 2 pi RL. I take a circumference, multiply by the length, and that gives me a surface area, doesn't it? And then I go out in dr, which gives me the next one. And it just boom, 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 like Russian nesting dolls coming out. Toilet paper rolls. So there's my dq. And now to get my charge, I integrate that dq. And what are my limits going to be? From 0 to whatever the radius of this thing is. So I plug everything in. 2 pi L comes out. And then I have A over R cubed plus B times R dr. You gave me rho, A over R cubed plus B. Oh, should we ask ChatGPT?
We could, because it has the reasoning too. Oh yeah, they did upgrade it.
Yeah. It's been getting a lot of stuff right.
Not for me. I had to really learn.
So it interpreted my integral correctly and then died. Why did it die?
Too many variables not accounted for.
Take A out?
Consider T a constant.
It's just a number.
Make B a constant, I guess. Would that help?
Usually it doesn't want the numbers. Usually it... Boy, this is really pooping out.
Try to make B a constant. See if that does anything.
Does this integral not have a solution? No. This has got to have a solution. There it goes. So it probably was having trouble with the time it was taking for the calculation.
Did you see that earlier? Yo, that shit was heinous.
I've noticed that with the new ChatGPT models that it takes a lot longer for it to come up with answers, but the answers are correct.
They're trying to do it the deep seek way.
I mean, not always, because I tried that for number 13, right? I got an answer wrong the first time.
What kind of hardware y'all got? 'Cause my ChatGPT be on that full.
Well, it's all running in the cloud, so it shouldn't be anything with your local computer. All right, so it's going to attempt partial fractions for a while. But we've got the setup, right, for that integral done. And of course, I would have checked any function I gave you to be a relatively simple integral to do. Or it should have been on the integral table. So what did it say? Whoa.
Oh, and it used Wolfram Alpha too.
Yeah, see, if I was writing the exam, I wouldn't have given a function like that. I had a feeling it was going to have a natural log in it, but I was surprised about the arctan. I'm not even sure that this is right.
I see the arctan.
It says you can verify. It's giving me the Wolfram Alpha thing.
And then
Please let me know if you need any further clarification.
What does this mean? Can you do this in French?
Can you do this in French? Is that your clarification? You have 4 apples. Take the integral. Doesn't know calculus. No calculus. You put it on the. Don't know French.
All right, this class has gone off the rails.
It just comes back to I don't know. Explodes. Do it.
Like finding the area under a curve. Third graders don't even know what a curve is. Anyway, other questions that are more pertinent to what's going on, instead of trying to fool AI models.
I'm kind of curious now to see what the is going on. I think you have a big chocolate
They low-key did it though.
Yeah, I'm right. That's pretty good.
With grown-up math tools.
Use special tricks.
All right.
Special tricks.
You should go on ChatGPT and ask it to explain Gauss's law to you like you were a third grader and see what it does.
Actually, yeah.
So do you guys remember the survey I gave you on my 4A students last year with the using ChatGPT stuff? There were a lot of excellent comments on there. One that I remember in particular really just grabbed me and it just put a knife straight through my heart. In a good way. The comment was, English is not my primary language. I use ChatGPT all the time to explain complicated terms in a way that I can understand. And then the student shared an example. I didn't know what a merry-go-round was. And they spelled it M-A-R-R-Y. Merry-go-round, right? And ChatGPT helped me to understand. And I didn't have to feel embarrassed to raise my hand and ask that question. I was like, bring ChatGPT on. Let's do it, right? For somebody that's struggling with terminology, especially if English isn't the first language, like, yes, this is perfect, right? I, of course, would love for the student to be able to trust me enough to come up and ask me what's a merry-go-round, right? But like, if they're not at that point or they feel embarrassed about it, by all means, right? It can be an excellent tool for stuff like that. So, and it's the new O3 and models. I haven't seen a miss a physics question I've given it yet. That's not true. I fed it the ladder problem this morning. You guys remember the ladder problem from 4A? I stopped it 5 minutes later because I had to come to class. Like I was just trying to kill time. I wanted to see if it could do the ladder problem. It was still said reasoning 5 minutes later.
And that was a homework question.
So later today, maybe when I get home or something, I'll just throw it on there and just see how long it takes to work the ladder problem. So, yeah.
You have to like break the ladder in half and do one side and the other.
Yeah,
I'm not gonna lie, it sounds so trivial.
but it was struggling. Any other questions? 5 minutes left. Feel like we've gone off the rails here. All right, if you have any questions, you can come up to me for the next 5 minutes. I'll be here. But other than that, I'll see you Thursday. Be here before class starts so you can get all situated and stuff.